Welcome back to The Explainer. I'm absolutely thrilled you're here. Today, we're bridging a pretty massive gap. We're going to connect ancient human curiosity about how things move all the way to that highly advanced piece of technology you're probably holding right now. Yep, we're exploring the incredible evolution of measuring motion. Let's get right into it.
So, have you ever stopped to wonder, how exactly does your smartphone know which way is down? I mean, really, you tilt it and boom, it instantly understands its orientation in space. We completely take it for granted, but the answer to that question is actually rooted in centuries of physics and some truly brilliant leaps in how we map our world.
Think about it like this. When you're playing a racing game on your phone and you tilt the screen to steer, you're not just playing a game, you're experiencing a direct application of some seriously profound science. Physics isn't just abstract equations on a dusty chalkboard. No, it's the literal concrete engine powering modern touchscreen gaming. It's happening right there in your hands.
Okay, let's dive into this. Here's our roadmap for today. 1. Beyond the straight line. 2. Drawing motion scale diagrams. 3. The math of motion. 4. Galileo's rebellion. And 5. Accelerometers in your pocket.
Section 1. Beyond the straight line.
So, the fundamental truth of our physical world is that it rarely operates on a simple one-dimensional track. The real world is messy, right? Motion happens in multiple directions all at once. Just picture a leaf falling from a tree. Gravity is pulling it downward, obviously, but the wind is pushing it horizontally at the exact same time. Or think of a cyclist leaning into a corner, or a sailboat navigating ocean currents and wind. To capture what's actually happening in reality, we have to look beyond straight lines. We really need two-dimensional kinematics.
Section 2. Drawing motion. Scale diagrams. Now, long before we had complex computers, early scientists and navigators had to physically map out this two-dimensional motion using visual tools. And actually, this is a method still taught to naval officers today. It's called the head-to-tail method. It works like this. Step 1, you draw your first movement, or vector, starting right from a central origin point. Step 2, you draw your second movement starting exactly where the first one ended, essentially joining them tip to tail. And finally, Step 3, you draw a brand new line from your very first starting point to your final ending point. That resultant vector, that new line, shows you exactly where you end up.
What's really cool about this visual method is how tangible it is. You literally take a physical ruler to measure the length of that final resultant vector and grab a protractor to measure the angle. So, say your scale is 1 centimeter to 10 meters. Well, a 9 centimeter line on your piece of paper perfectly equals 90 real-world meters. It's essentially a physical map of movement.
Section 3. The math of motion. But, while drawing vectors on paper is wonderfully visual, it does have some strict limits. I mean, imagine a ship making 50 different directional adjustments over the course of a week. Drawing 50 tiny arrows tip to tail is incredibly cumbersome. Plus, one slight slip of your pencil and your final measurement is dangerously wrong. That is exactly why we moved to algebra. Breaking every movement down into strict perpendicular parts gives us absolute precision, and it's that algebraic approach that makes modern tools, like the GPS in your car, actually possible.
This is actually where the math you learned in grade school perfectly maps onto the real world. By breaking vectors down into perpendicular components, pure north-south and east-west lines, we create perfect right triangles. And from there, the Pythagorean theorem calculates the exact distance, and basic trigonometry, like the inverse tangent function, calculates the exact direction. Suddenly, a jogger's route or a sailboat's complex path across the sea becomes an exact, calculated science. It's a real game changer.
Section 4. Galileo's rebellion.
Now, understanding the how of motion is really only half the story. We also need to talk about the who. For centuries, the ultimate authority on all of this was Aristotle. But his theories relied on pure logic. For example, he claimed that heavy objects naturally fall faster than light ones. And honestly, it sounded logical, so everyone just accepted it as fact. But jump ahead to the 16th century, and along comes Galileo. He took a totally radical approach, experimental evidence. He basically argued, hey, you can't just think your way to the truth, you have to actually test it.
But testing this was tricky. Objects dropped from a tower fell way too fast for anyone to measure with 16th century tools. So Galileo came up with a brilliant workaround. He used inclined planes, basically ramps, to essentially slow down gravity. Rolling bronze balls down these ramps let him accurately measure both time and distance. And his groundbreaking discovery? He found out that the distance traveled wasn't just tied to time, It was proportional to the time squared. He proved once and for all that falling objects don't just move at constant speeds, they accelerate.
Galileo's reliance on hard, measurable data instead of philosophical logic completely ushered in the modern era of science. Albert Einstein himself wrote about this, saying, quote, "All knowledge of reality starts from experience and ends in it." He is the father of modern physics, indeed of modern science altogether. Galileo proved that the universe follows mathematical rules that we can actually test and verify.
Section 5. Accelerometers in your pocket. And that verified measured data, that's exactly what powers our modern world. All those kinematic equations, the vector math, Galileo's understanding of acceleration, it's all now physically embedded into a tiny piece of hardware called an accelerometer. Usually made of semiconducting material, this tiny electronic device precisely measures how quickly something is moving in a particular direction. It literally calculates acceleration in 2 or 3 dimensions simultaneously.
Now, what's really interesting about this slide is the sheer difference in scale here. On one side, we have the massive, immersive digital world of a racing game on your phone. And powering it? A 3D accelerometer microchip resting right on a fingertip. I mean, it's literally only a couple of millimeters long. Centuries of vector math and Galilean acceleration have been miniaturized onto a tiny speck of silicon. How wild is that?
These chips are constantly working in the background of our everyday lives. They convert physical gestures, like swinging a virtual tennis racket, into video game mechanics. They're what automatically rotates your screen when you turn your mobile device sideways. But beyond just entertainment, they're actually embedded in ordinary laptops to create massive broad-area earthquake detection systems. By sensing sudden, accelerating shifts in the Earth, these tiny chips are actually helping save lives.
So as we wrap up this explainer, I want to leave you with this thought. The next time you round a corner on your bike or simply tilt your phone screen, ask yourself, how are the invisible arrows of two-dimensional kinematics secretly guiding your world? Because the history of science isn't just stuck in the past, it's calculating and accelerating in the palm of your hand right now. Keep observing, keep questioning, and we'll see you next time.